Okay, so when we left off, we did an example where a lever was pivoted right in the middle. That was where the fulcrum was, and we saw how much force it took to balance, how much force it needed to be exerted on one side to balance something that was on the other. And it turned out that the forces had to be equal. Well, that's not going to be the case if we move the fulcrum, the pivot point, around. So let's take a look at C. Now the fulcrum is moved so that it is 0.25 meters away from the worker. How hard must he push in order to support the 20 kilogram object? So let's draw another picture. Here is our object. Okay, here's the lever. Remember, the worker's pushing down over on this side, and now the pivot point is over here, only 0.25 meters away. There's still a tray over on this side with a mass on it. That's going to cause a force of gravity downward. There's going to be a normal force upward from the pivot point. And at the center of mass is still the force of gravity from the board. So that's why this is going to be different. One of the forces moved, okay? The normal force moved, but the force of gravity for the board did not. And let's put our axis on there. Okay. So, we still need to figure out the axis of rotation because ultimately we are trying to figure out what F is. We don't know what the normal force is, we don't know what F is, so this is not going to be something where we can just do a forces analysis. But we can do a torques analysis because remember, with a torque analysis, depending on where you put the axis of rotation, you can actually cancel out one of the torques. So right now, we are going to move our axis of rotation. So it cancels forces we don't know. And in this case, that's going to be Fn. We're going to set our axis of rotation right here to cancel out that torque. So, since the axis of rotation is at the fulcrum, there is no torque from the normal force. Let's get into our net torque equation. Tau net equals the torque from the object. Let's see, that's going to be counterclockwise, so that's positive. TO plus the torque from the board's weight itself. That now is a distance or a displacement R from the axis of rotation, so that now is providing a torque. So I'm going to call that tau B minus the torque from the force from the worker because that tends to rotate things clockwise. We're trying to balance this, so again, the acceleration is 0. That's going to be the case for a lot of torque problems, but I promise you will see some problems where there is an angular acceleration. Okay, so we know that since the net torque is 0 because the angular acceleration is 0, the counterclockwise torques must balance out the counterclockwise torques must balance out the clockwise torques. So that's going to be RO FGO sine theta O plus RB FGB sine theta B equals RF F sine theta F. Now we are trying to calculate, let's see, we are trying to calculate F. That's what we're looking for here. We know that we can figure out the distance that the object is away from the axis of rotation. If it's 0.25 meters from the worker, and this whole thing is 1.5 meters long, then it must be 1.25 meters from the plate, where the mass is, to the axis of rotation. So that's going to be 1.25 m times the force of gravity from the object. We know that already. That's up here. That's 200 newtons. That force is perpendicular to the vector r, so this is going to be 1. Matter of fact, all the sine theta is going to be 1. I promise it won't always be like that. On the next sheet, we are going to see a case where it's not. Those are all 1. How far away is RB? So RB is the distance or the displacement from the axis of rotation to where the center of mass is, because that's where the force of gravity on the board acts. If half of the lever is 0.25, excuse me, is 0.75, and the axis of rotation and the fulcrum is 0.75 from the worker, or 0.25. Oh, excuse me. Then the center of mass, where the force of gravity acts, must be 0.5 away from the fulcrum, 0.5 meters. We haven't calculated FGB yet, but I will do that right now. Equal to the mass of the board times G. Let's see, and that's equal. The board is 5 kilograms times 10 meters per second squared, 50 newtons. So 0.5 times 50 newtons equals, the force from the worker is 0.25 away from the pivot point from the fulcrum. That's where our axis of rotation is. So that's 0.25 times F. 200 times 1.25 is 250. 0.5 times 50 is 25. 0.25 F. We add those two things together. We divide by 0.25, and we get that the worker must actually use a force of 1,100 newtons, 1,100 newtons, to support that 20 kilogram mass. That's a lot of force. That's way more force than we needed over here. But that's due to not only did an additional torque appear that it had to balance, but if we move the axis of rotation this way, then that means that these torques over here are now bigger than they were before. So the worker really has to push really hard there to support our mass. How much mass can the worker support if he now stands on the bar? Let's get our net torque equation going again. Torque from the object plus the torque from the bar minus the torque from the person's force equals I alpha, but that's 0. RO FGO sine theta O. Again, we know that's 1. RB FGB sine theta B. RF F sine theta F. So this time the worker is standing on us. Remember, the force that we're exerting is 850 newtons, equal to his weight. We know all the R's are the same. We know the force from the bar is the same. The only thing we're looking for here is the mass of the object that can be supported. Coming up here, we have 1.25 times 10 meters per second squared times MO. I'm going to put an O there. Forgot that first time. Plus 25 equals 850 times 0.25, 212.5. Let's see, this ends up being 12.5 MO. Equals, let's see, 187.5. If the worker stands right on the bar, they can support a mass of 15 kilograms. So interesting. I mean, we're reducing the force. Before, in order to support a 20 kilogram mass, they needed to use 1,100 newtons of force. To support a 15 kilogram mass, they can do that with 850 newtons of force. Kind of crazy. All right, let's see here. Was that actually? Okay. Now, so that's if it's a very short arm, that's what happens. Now let's say we move the fulcrum one more time, so that's 0.15 meters away from the object. So we're going to draw our setup one more time. There's still going to be a force over here. Still going to be a force of gravity from the board right here. Still going to be a plate over here with an object. That's still going to give a force, FGO. But now the pivot point is right here. And so that's where the normal force acts. And since the axis of rotation is at the fulcrum, or at least that's where we're going to set it, we don't have to worry about the torque from the normal force. And that's key here, because right now, again, just like in A and C, we're trying to see how much force the worker needs to support this object, this 20 kilogram object. Let's do our net torques. Okay, again, this time, we're still going to have a torque from the object that is counterclockwise, so that's positive. This time, the torque from the board is going to be negative because that would tend to rotate the system clockwise, minus the torque from the board, and then minus the torque from the worker, because that would also tend to rotate it clockwise. No acceleration. Therefore, RO FGO sine theta O equals RB FGB sine theta B plus RF F sine theta F. And again, you shouldn't just automatically cancel these out to be 1. I'm just trying to save us some time here. In every example we've done so far, the R, the vector from the axis of rotation to where the force acts, has been perpendicular to the force. That's not always going to be the case, but it's been the case every single time so far. And it very clearly is based on the geometry here. Let's see. We know the size of each of these forces, and we know, except for F, that's what we're looking for, and we can figure out the displacement vectors R. R for the object. The pivot point is right here. It says it's 0.15 meters away from the object. So R, 0.15 meters, times the force of gravity on the object, that is 200 newtons. That's equal to, if half of the lever is 0.75, and this right here is 0.15, this must be 0.6. So I have 0.6 meters times, let's see, the force of gravity from the board is, I did it up here, 50 newtons. Plus, if this is 0.15 and this whole thing is 1.5, our F must be 1.35 meters times F. How much force is needed? We're going to solve this. I'll bring this up here. 200 times 0.15 is 30, equals 0.6 times 50, 30, plus 1.35 F. I subtract 30 from both sides, I get 0, and then I divide 0 by 1.35. I actually find that no additional force is needed. This is a really neat result. This is perfectly balanced without even a force F. It's balanced because the torque from the board is equal to the torque from the object with nothing else needed. So you can actually set up this system so that the board itself balances out the object on the other side. Kind of neat. How much mass could the worker support now if they were to stand on the bar? Set up our net torque equation again. Let's see, RO, 0.15 meters times the mass of the object times G equals 0.6 meters times 50 newtons plus 1.35 meters times force of the man, if he stands there, 850 newtons. If the person stands on it at this point, they can support 785 kilograms with just their weight of 85 kilograms. Now, that's pretty interesting. Okay, so depending on where the fulcrum is, where the pivot point is, where that normal force acts, that might change how the torques act and how they support or don't support the object. Now, there's got to be a trade-off. If you're looking at this and you're like, oh, well, why wouldn't you just put it over here all the time? Well, let's think about it. If you did this and you were trying to move this object up or down, you would have to move this, just look at the geometry, through a huge range to offer a tiny little bit of change in the height here. On the other hand, here, where there's a huge force from you might move this up and down just a tiny little bit, but it's really going to either push this up or lower this down. This is kind of the beginnings behind how levers work. We're not going to do too much more with that, but I did just want to show you that the torques depend on the axis of rotation, and just changing where an object is pivoted can actually change those torques very substantially. We're going to move on to our last topic, which is what to do when theta is not 90 degrees. So let's say that you have a lever. You push directly up on the left end of a lever that looks like this. Let's focus that a little bit better. Okay, there we go. So you're pushing up like this with a force of 50 newtons. And you have, this lever is 2 meters long. If you push up with a force of 50 newtons, what's the torque that you generate? Well, we know that torque is equal to RF sine theta. R, in this case, the distance from the axis of rotation, it's pivoted right here, to where the force is applied is 2 meters. The force itself is 50 newtons. The angle part is going to be the tricky part, because this right here, okay, from the axis down to where the force is applied, that's R. In order to figure out the angle, we need to write these two vectors tail to tail. That would look something like this. And if you think about it, or imagine just bringing this one up here, we know that this right here is a 60-degree angle. We know that this, from this vertical line upwards to this dashed line going downwards, must be 180 degrees. This angle, therefore, is 120 degrees, times the sine of 120 degrees, 2 times 50, times the sine of 120, we get a torque of 86.6 newtons times meters. Not too hard, you just have to remember to change your vectors around so that you can line them up like this. Now that method works a lot. Actually it works every single time, but sometimes it's a little tricky to figure out how the vectors are acting. So there's a couple other methods that we can use. Another way to calculate this when the angle isn't very obviously 90 degrees might be to find the magnitude of the component of the force that is perpendicular to R. We symbolize that with F and then a little perpendicular sign, upside down T. So if this right here is a 50 Newton force, and this is R, and we know that's 2 meters, then think about this. We could have components of this, one that is perpendicular to the force, I'm going to call that F perpendicular, and another one that is in line, or excuse me, not perpendicular to force, but perpendicular to R, and we have another component that is in line with R. Okay, I'm not going to call that one anything. I hope you notice that we have a straight line here, another straight line, or at least would be straight line here if it went all the way up, and we have a transversal, something cutting across both of them. If this angle is 60 degrees by geometry, this angle has also got to be 60 degrees. What the perpendicular force component says is that we should be able to calculate a torque by taking R and multiplying by the perpendicular component of the force. That should tell us the torque. Okay? This is a little bit different from RF sine theta. It's skipping over the sine theta part, but you'll see where that comes in just a little bit. R times F perpendicular would also work, and it makes sense because it's kind of like saying if you take the R, the vector from where the axis of rotation is to where the force acts, and that's multiplying it by a force that's perpendicular. Well, if R and F are perpendicular, then it's kind of like, oh, that sine theta term that usually is here seems to have gone away. But the perpendicular component of a 50 Newton force obviously is not 50 newtons. We need to calculate what that is. If you look here, here's 50 newtons, this is a 60-degree angle. This component is the opposite side of that right triangle. If it's opposite side, then that means that this component can be calculated using sine theta. So the perpendicular component is actually the force times the sine of theta, where theta is 60 degrees. And wouldn't you know, if we make that substitution, we are right back where we started. 2 meters times 50 newtons times the sine of 60 degrees. Almost back where we started. Let's see if we get the same thing. And we do. So we see that finding the perpendicular component of the force can also be useful. I'm going to show you one more method to calculate the torque when the angle is not very obviously, the angle between R and F is not very obviously 90 degrees. And I alluded to it before in a few videos ago. It is known as the line of action method. The line of action is an imaginary line that overlaps and is parallel to the direction in which the force acts. So you draw your line of action, and then you are going to find the spot where it is closest to the axis of rotation. So I'm going to draw my force in here. There's my force. F equals 50 newtons. The line of action is an imaginary, so we're going to put dotted line that goes in the same direction as the force. We want to use the distance where the line of action is closest to the entire, or where the, we need to use the distance, from the axis of rotation to the line of action. That would be right here. Okay? Right here. This is our distance R that we're going to use. And look at that. F and R are very clearly perpendicular to each other. We don't have to worry about that. This is kind of what I was just saying. The new R will be perpendicular to the line of action. So it will be parallel to the force. So theta ends up being 90 degrees in the equation RF sine theta. So really this time we're not doing F perpendicular, we're doing R perpendicular. Okay? Because R perpendicular and F are obviously perpendicular to each other, that takes care of that sine theta that would otherwise be there. But once again, when we go to calculate what R perpendicular is, the actual R we know is 2 meters. This R would really be over here in the triangle. It's opposite this 60-degree angle. Therefore, we can figure it out by using the sine of 60 degrees. So R equals, or R perpendicular, that's what this is, equals R times the sine of 60 degrees. I'm going to put that in here. R sine of 60 degrees times F. Well, you know what the result is going to be. 2 meters times the sine of 60 degrees times the force of 50 newtons. It's the exact same thing we've had these last few problems. The torque is 86.6 newtons times meters. Now, you might be saying, why did you bother showing us all this different stuff? What I wanted to show you was that these are 3 different ways to calculate torque. And each is useful in different situations. Each of these is useful in different situations. Matter of fact, when I was coming up with the answer key for the torque homework, I actually used each of these different methods at least once, and they worked out. Okay? So a lot of times the first one is great. I also use the line of action method a decent amount, and the second one I don't use as much, but it works just as well. Whenever you have to calculate a torque and the angle is not very clearly 90 degrees, you use one of these methods. That's pretty much it for torque. The next stuff that we will talk about is how torque plays into what we call rotational dynamics. It's kind of like looking more in depth at objects that do have angular acceleration and have torques acting on them. It's really neat. There's a lot of neat applications, but we will get to that in the next few videos. So bye for now.